So over the last several weeks, I've been battling my computer with like some resource issues where I keep running out of space on my hard drive, and I finally have figured out what's going on is that with all these shared notebooks that I have on my end, my computer builds like a backup for everybody's shared notebook of everything you have in it. And it's chewing up like, 50% of my hard drive doing this. So I need your guys' help to like weed that down a little bit. So what I'm going to ask you guys to do is to just move anything that's not like actively being used into your own non-shared notebook. So for example, let's pick on Abby. So Abby has like this syllabus tab not being used. We could move that. The reviews tab, well, that's empty. We could just delete that. And then in this chapter 1 tab, we have everything that we've been working on for the entire semester. Well, everything that's not chapter 4 could certainly be moved. And even the things in chapter 4 that I've graded that are no longer like an active assignment, you could move. And I went and graded your guys' homeworks this morning, so you should see some check marks on those things. So the easiest way to move these pages when we have a bunch of pages, but maybe we don't want to move all of them, is if I click at the page on the top, and then I hold down the shift button, and then click at the page at the bottom. It'll highlight all the pages for us. And then say there's some things that I want to save. So like maybe worksheet 3 we haven't done yet. I can hold down the control button and I can click like worksheet 3 and it unhighlights just that one. And maybe I want to save like the odd solutions in the chapter 4 problems because I'm still going to use those things too. So again, still holding down control, I can click on those things. But everything else I can move somewhere else, right? So I can now right click on all that stuff and select cut. And it'll cut all those pages out. And if I go back up into the OneNote notebook that's my own private notebook, I can make a page for my 5th hour trig and honors trig class and right click in this pages and hit paste there. Elizabeth? So I pressed the shift button to do the highlighting. So if I was at the top of the list, I hold down shift and click the bottom of the list. That highlights everything. And then if I hold down the control button, I can unhighlight just like 1 or 2 specific things, which makes it a heck of a lot easier to move everything than trying to go individual section by, individual page by individual page, just like cutting and pasting. Is that what you needed, Elizabeth? Okay. So this was something that I didn't kind of anticipate at the beginning of the year when I set up the system. I didn't realize that OneNote was going to build a backup for every single thing that's on all of your computers on my computer. So having like 200 of these shared notebooks is like kind of impossible. Like I don't have enough space to like even record a lesson to post later. So I've been playing a shell game of like deleting these temp files to do a recording, but by the time I finish the recording, the temp files have refilled because I'm using OneNote to do it. So it's resyncing and like refilling all these temp files in, and it just becomes like a shell game of moving around this memory space from the trash can to OneNote. And I'm just like, feel like I'm fighting with my computer the whole time. Obviously, if you have any issues doing what I'm asking you to do or not quite sure, feel free to ask. I'm happy to look at what's going on with your computer or, just kind of show you again or whatever it is that you kind of need. But this will be a big help if we can get this kind of straightened out. So I appreciate you guys helping me with this. And kind of from here on, as you do homework assignments and I grade them and they get check marked on them, if we can get in the habit of moving them into our private OneNote, or you could just delete them, like I don't care what you do with them after I've graded them. Probably a good idea to hold on to them. There's like a semester exam and all that stuff that you have to worry about, so they may be helpful for that. Or even if it's a situation where it's like I make a mistake and I didn't record something that I should have, that you have like, hey, this is the paper that that I thought you graded, but I guess you missed or whatever. Like plenty of you have seen me make mistakes on that kind of stuff before, that you've been like, you marked this missing and it's done. It's like, oh, okay, well, let's fix that. So I would hang on to all that stuff, but you don't have to. It's your stuff. And I think by and large, I don't make a lot of mistakes in terms of grading things, but it does happen from time to time. And, I think Abby G's had it happen a couple of times already this semester, and is probably pretty sick of me missing her things. I don't know why it keeps happening to her and not to anybody else, but it's not personal, Abby. But you're doing the right thing, and it's like saying, hey, this is done, so can you just double check? And that's great, like no problems there. Has somebody feel like they've finished moving everything that they're supposed to, so we can just kind of take a peek at it? Anybody? Okay. So Elizabeth, you said you did? Felt like you were finished? And so I look and everything is still here right now, but it's probably a sync issue where, there's two syncs that are happening. Your stuff has to go up to the cloud to tell it there's nothing there, and then I have to go pull it back down. And if I go look now, there's basically nothing left. So that's excellent. And this will help a lot on my end. As of right now, I don't plan on moving anything from the content library. Like I'm going to try to keep everything in the content library here. And I don't think it'll be an issue, but if it does become an issue where I have to move this stuff too, I'll let you guys know in advance. So if you want to take the content library from here into your private notebook before I go and like warehouse it on PowerSchool or something where it's a little bit more of a hassle to like look at what it is before you have to download it and try to figure out where you're going on your computer and all that, because I know that this is very convenient for file sharing purposes to just have it all in the content library where you can look at the thing and be like, oh, that's the one that I want, and then take it, as opposed to going to PowerSchool where all you have is the title of the file that you can either download or not, and you can't really look at it beforehand, and just kind of a hassle. I think it'll be fine leaving everything in here, but it's a long semester and the content library will be quite large by the end of things. But if I have to move it or whatever, I'll let you guys know in advance. So if you want to take the whole thing before it becomes like a chapter by chapter, like I can only have one chapter of content library here active at a time, I'll let you know. Okay. Is anybody still working on getting things moved? Okay, very good. And obviously, if you run into a situation where it's like, oh, I needed this thing, you can always move it back, kind of doing the same process. You can just, cut and paste, or even copy and paste the pages, over, and it's not too difficult. OneNote makes it pretty easy to do that. Okay, cool. So today we're going to continue talking about chapter 4. So we have 2 more sections in chapter 4 that we're going to talk about today. And then that'll kind of finish up chapter 4 for us. And we'll talk about what the rest of this week and next week will look like here at the end. But so section 4.2 is titled Problem Solving. And when we say problem solving, what we're really meaning is just like kind of doing story problems, for lack of a better word. And the biggest thing with story problems kind of in this section, or really kind of in general, is being able to like draw a useful picture to kind of describe the situation that's happening. So that'll be of particular importance to us here. Before we do some examples, though, let's define a couple of important phrases. The first is angle of elevation. I'm not going to define this in words. I'm just going to define it with a picture because I think it'll be more useful to what it is we're going to use this for. So let's say on the ground, looking straight forward ahead. So that's like their line of sight. And that would be generally parallel with the horizon, or with the ground, right? If you're standing on flat ground and you're just looking straight ahead. And let's say up in the sky there's like a like a person in like a hot air balloon or something. And they decide to look up. Person. This is our elevation measured from their line of sight up to that object they're looking at in the sky. Now, the opposite of this is the angle of depression. So if we imagine the person in the hot air balloon, they're looking straight ahead. And they move their neck down, so they're looking at their friend on the ground. So that would be the angle of depression. So again, an angle of depression is the angle that's like between their line of sight and whatever they're looking down at. And the angle of elevation is from their line of sight to whatever they're looking up at. And that's the vocab for this section. So let's just do a couple of examples where we practice kind of drawing a picture and then solving the situation. Is that a sneeze? God bless you. You're welcome. Okay. So my first example says, Christy is looking up at the Fisher Building in downtown Detroit. She is standing 200 feet from the base of the building and finds the angle of elevation to the top of the spire to measure 66 degrees. How tall is the building? So I'll draw a picture. Here's Christy. There's my building. Looking up to the top of the spire, there's my angle of elevation then. And it says that she's 200 feet away. And we're looking for the height of the building. Everybody okay here? So this really just turns into a right triangle problem. Since I know that a building is typically built perpendicular to the ground, other than those Italian builders, that's a Leaning Tower of Pisa joke, not anything specifically against Italians. So, to solve this for x, what do we need to use? Tangent, right? Tangent is opposite over adjacent. So if I solve for x, I get x is equal to 200 times tangent of 66. And if I bust that through my calculator, I get about 449.21 feet. What do I have to be careful about, though, when I'm typing this into my calculator? Got to be in degree mode. Yep, how did we know it was in degree mode? The angle given to me in the problem was in degrees. It tells us. So this section in particular, or the chapter in particular, we have to be careful because there's going to be times where we need our calculator in radian mode, like we did on worksheet 2. And there's going to be times where we need our calculator in degree mode, like on this worksheet 3. And Lord knows on the test they're going to be potentially out of order, so you're going to have to switch back and forth. So just be cautious about that. That's something to kind of keep an eye on. Any questions with this first example, though? Hopefully that feels pretty easy. Let's do another. Jane has climbed a tree and is looking down at her friend Mary. Jane has climbed 17 feet into the air, and the angle of depression to Mary is 49 degrees. How far is Mary standing from the base of the tree? Okay. So here's Mary up in the tree. Jane is up in the tree. And here's Mary standing on the ground. We're given that our angle of depression is 49 degrees. And the height of this tree is 17. And we're asked how far is Mary standing from the base of the tree, so we're looking for this side here. Now, keep in mind that what we really have going on here is a rectangle, right? So I can think of this side as x also. We're really just trying to solve this triangle for x, right? Which trig function would I use here? Tangent, because it's opposite over adjacent. I cross multiply, and I get x times tan 49 is equal to 17. And then if I divide by tan 49 to both sides, and type that into my calculator, I get about 14.78 feet. Any questions so far? So far, this should feel pretty easy, right? The solving aspect of it. Maybe the trickiest part is getting the drawing done correctly, but if you can do that, it's usually pretty easy. This one's going to be a little bit more challenging, the one in which we can probably handle. Claude and Simone are riding bicycles in Paris. At one point, they look up and measure the angle of elevation to the top of the Eiffel Tower to be 32 degrees. When they, I guess I just missed the Y there, pedal 100 meters closer to the tower, the angle of elevation changes to 37.5 degrees. How tall do they estimate the Eiffel Tower to be? So here's my Eiffel Tower. Okay, so our first spot, we got our angle of elevation to be 32 degrees. We did it again later, and as we got closer to the tower, and we got 37.5 degrees. And we're told that we went 100 meters closer. So this is our situation. Do you guys buy that? I think describes what happened in the words pretty well. So when you look at this picture, how many right triangles do you guys see? Hopefully you should see 2, right? Angle is 32, 37.5. Let's call this side x, since we don't know that, and we'll call the height of the pyramid 8, or the tower h. Now, what would I write down as the length for the other leg of this 32 degrees triangle? 100 plus x. Everybody agree that this is taking the situation I had above, and I just broken it apart into 2 right triangles. We all okay with that? So notice we have 2 unknowns in this situation, right? Everybody agree there? How am I going to solve a situation where I have 2 unknowns? Exactly right. I need to form a system of 2 equations. So for this first, I can say that tan 32 is equal to opposite over adjacent. And for this triangle, I can say tan 37.5 is equal to opposite over adjacent. And then I'm going to cross multiply because fractions, yuck. Let's get rid of that. That'll give me this as my 2 equations in my system. Now think back to your algebra class last year. How did you solve a system? Or what were some of the ways you used to solve a system of equations? Substitution, elimination, and you probably talked about some matrix methods as well, right? Which appears to be the easiest one to use in this particular situation? Substitution, because we already have the variable isolated. You guys agree with that? So since both of these are equal to h, I can go ahead and take the right-hand sides and set them equal to each other. Everybody's okay there? Now to solve for x, I have to get the x's on one side, so let's distribute this tan 32 through. And then I'm going to subtract the tan 32 to the other side. Or I'm sorry, the x times tan 32. I'm going to subtract to the other side. And I notice on that right-hand side now, both of those things contain a factor of x. So I'm going to factor that out. And then I'm going to divide both sides by that difference of tan 37 and tan 32. So when I type that into my calculator, I get about 438.64 for x. I guess these are meters. Was that the quantity that the question asked for, though? I think the question asked for the height of the Eiffel Tower. If I go back to my picture, did x represent the height? Nope. So to solve for the height, I'll just go back and plug it into one of these original two equations. I'm going to choose to do that one. Yeah, or times where maybe you have to break it into two triangles and solve a system like this. What do you think about this section? It's all right? Okay. Cool. Let's talk about section 4. This is about applications of, and really what we're talking about in this section is vector problems. So do you guys remember from your geometry course what a vector is? A vector is a mathematical quantity that's described by two parts, a length or magnitude, and then a direction. So we had mentioned navigation as being one of the primary applications that, or ways that we can use a vector to make life convenient. Unfortunately, the way that, like people that fly planes or drive ships or pilot ships, is that maybe the word? I don't know what it is. Anyways, the way they describe their bearings or their direction is not the same way we will when we define sine, cosine, and tangent, which is really inconvenient. So let's talk about the difference. So our course or bearing of an object is given as an angle of the object's line of travel measured clockwise from due north. So let's say that we have a bearing of 58 degrees. Okay? So remember, if you're looking at a compass, there's north, northeast, southwest. So a bearing of 58 degrees, we're starting at due north, and we're going 58 degrees. So that's our bearing. Everybody okay with that? Let's convert that bearing into an angle of rotation like we've been using in this class. So our angle of rotation is going to start at the positive x-axis and go counterclockwise. What does the angle of rotation have to be in this situation? (32 degrees), because I know that one quadrant is 90 degrees total. So those have to be complementary. Let's do another example. Let's see say our bearing is 164 degrees. So again, we start at due north, and then 74 more. You agree with that? Now our angle of rotation is going to start here and go to there, right? So I have 90, 90, 90, and then that little bit more. How much is that little bit more going to be there in the fourth quadrant? Has to be 16 degrees, right? Why 16? Yeah, the quadrant is 90 degrees and 16 is the complement of 74, right? So our angle of rotation is 90 plus 16. So that's 286. Why do we want these angle of rotations? Because if I have to use sine, cosine, or tangent in doing one of these problems, I have to use it on an angle of rotation and not a bearing. Because the way we defined sine, cosine, and tangent was with angles of rotation. Our navigator friends should have gotten on board and changed the way they're describing their directions, but they haven't, so we're forced to do this. Does anybody have any questions about how we kind of convert back and forth between degrees and bearings? For the most part, you just kind of draw the picture and figure it out, right? It's not too difficult. So let's do an example, and we'll kind of talk through how to do this. This is a kind of a problem that you would have done in your geometry class, and we'll use some vector techniques that we developed in those geometry classes, but it was a long time ago, so we'll kind of re-explain some of those finer points as we go, but we're going to do it in the midst of doing an example. Is that okay with you guys? I typically find that goes, especially when we're doing things that we've already kind of done before, but it's been a long time. It usually goes a little bit better with a concrete example to work from rather than just going and rehashing the same old lecture that we've done. So here the example says a boat leaves a port and averages 40 knots. A knot is a nautical mile per hour, so it's a speed measure of speed, for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to the starting position at the port? So what I'm going to do is, when I read this problem, I read two vectors. So there's the first vector, which is the first leg of our journey. And then I have a second vector that's like the second leg of our journey. Everybody okay with that plan or that observation? Okay. So I know that my final location of the boat can be described with a vector by taking the first leg of our journey and adding the second leg of our journey. And I'll put the little ray on top of it because that's usually the symbol we use to indicate that something is a vector. Everybody okay with that reasoning? Okay. So if you guys remember back to your geometry class, one of the ways that one of the other ways we can represent a vector other than with magnitude and direction is with something called component form. The component form just describes the location of the end of that vector. So a vector has a magnitude, a length, and a direction. So it's just describing like the xy coordinate where the end of that vector is located. Everybody is okay with that idea? So that's what we're going to do here first, is we're going to translate these vectors that have been described as magnitude and directions into component forms, because it makes the vector addition trivially easy to do. So for vector v1, the first thing I'm going to do is I'm going to take its direction that we were given and convert it into an angle of rotation. So we have 215 degrees, so 90, 90, and then 35 more. Everybody's okay with that? So my angle, and then that other piece, which in this case is going to be 55. So 90 plus 55 is 235 degrees. Is everybody okay with that? All right. So I'm going to take my vector 1 and break it up into an x coordinate and a y coordinate. The x coordinate can be found by taking the magnitude of vector v1 and multiplying it by cosine of the angle of rotation. Similarly, for the component, the y component, it's going to be the magnitude of the vector times sine of that angle of rotation. What is the magnitude for vector v1? So it's 80 miles. That's 20 knots or 40 knots for 2 hours. That's our magnitude. And our direction was this 215 degrees. So here we're going to have 80 times cosine 235 and 80 sine 235. Haley?
How do you know that 40 knots is 50 miles?
So 40 knots is miles per hour.
Oh.
So 40 miles per hour for 2 hours is going to give us 80 miles. Is that okay?
Yeah.
Elizabeth? It's just dir for direction. So again, the vector has two parts to it. It has a magnitude and direction. Or you can represent it as an x and y coordinate, which is basically what we're doing here. So our alternate representation, the one that we're going to use to do the vector addition, is going to be that. And we use the wedged brackets rather than parentheses to describe this component form to indicate to us that this is a vector and not a point that we're talking about. That's just a notation piece. Everybody okay so far? Elizabeth? So on the unit circle, the x-coordinate is cosine of theta. Same reasoning here. Is that okay? It'll always be that way. X will always be cosine, y will always be sine. So let's repeat that same process with V2. So V2, we were going 55 knots for 3 hours. So our magnitude is 165. And our direction was 162 degrees. And just like before, I'm going to convert that direction into an angle of rotation. So 162 is like 90, and then 72 more. So there's where our vector is located. And now to get that as an angle of rotation, 90, 90, 90, and then a little bit more. That little bit more in this case has to be 18 degrees. So our angle of rotation be 270 plus 18, or 288 degrees. Once I have that, the x-coordinate of vector 2 is going to be magnitude times cosine of the angle of rotation. And the y-coordinate is going to be the magnitude times sine of that angle of rotation. So we can say V2 then is the component form this. So far, so good? Okay. So remember that we said the resultant that we were looking for was going to be the sum of V1 and V2. The beauty of having our vectors in component form is that we can add them component-wise. So we can just add the x-coordinates together, or the x-component together, I should say, and then the y-component together. Oops. That's that right. That's what it is. Everybody okay with where these numbers came from? I got the x-coordinate by doing 80 cosine 235 plus 165 cosine 288. And similarly for the y-coordinate. Okay. So what is that representing? That's representing our boat being like down here. Everybody's okay with that? So our magnitude is just going to be the length of that vector. Well, since it's starting at 0, 0, that distance is really just the Pythagorean theorem. It'll be that way like every single time. Is everybody okay with that idea? And my direction is going to be this, right? So that's 90. And this is just like phi. So just like we did before on worksheet 2, to calculate that phi, we're going to do the inverse of the absolute value of whatever that is. Now, when we calculate a direction, we're always going to be using tangent, because what we have is a y-coordinate and an x-coordinate. So when I type that in, I get 8869. Direction is 90 plus 80. Well, let's just write down phi, which works out to be a direction of 178.69. Or if I wanted the angle of rotation, depending on what it asks for, that would be 90, 90, 90, and then 1.31. But I think it wanted a direction rather than an angle of rotation. If I do recall, those were the quantities that they were asking for. So let's just go back through that and summarize again the process that we used, because it took a little while to get to the end, right? Probably doesn't hurt to go back and look at it again in broad strokes. So what I did is I took each of the vectors described in my problem, and I transformed them from being in the form of magnitude and direction into this component form. In order to do that, I had to translate from a direction into an angle of rotation, and then calculate the x and y coordinates for that vector. I did that for each vector. Important in doing that is that I drew these pictures, so I was able to figure out the angle of rotation. Very difficult to find that angle of rotation if you're not drawing the picture to look at it. I have a hard time visualizing that in my head. And I think the picture is extraordinarily helpful to get a sense of like what it is that you're doing. Once you have the component forms for all of your vectors, you add the component forms, component y, so the x coordinates get added and the y coordinates get added. That new component is the location of our new or our resultant vector. So we can graph that and then calculate its magnitude and direction. The magnitude we can just use the Pythagorean theorem on, the square root of x squared plus y squared. And to calculate the direction, we can use the technique similar to what we did in worksheet 2 by kind of drawing what it is that the angle that we're looking for and then finding the relevant feet. We're going to stop here because, well, that was a lot of stuff that I just kind of burnt through, and it feels like that's probably good.